There we go. Okay, so this right here, this goes back to our last 2 units ago now. Unit 4, I believe, when we were looking at experiments, sampling, simulations, all that fun stuff. So if we go through this real quick, we've got careful analysis of a given sample will indicate whether or not it is random. No, we can't just look at something and know that it's random. Sampling error implies an error, possibly very small, but still an error on the part of the surveyor. And I actually can't recall, very few of you, maybe none of you guessed this one. That's good. Sampling error is a natural part of any sample, and that's just the difference between the true population parameter and your sampling statistic. It's going to be there. It doesn't mean you did anything wrong. Data obtained when conducting a census are always more accurate than data obtained from a sample, no matter how careful the design of the sample. Theoretically, it's true, but it's not always true because of the complications with the census. Sometimes you can have undercoverage, even though you think you're getting a census. And sometimes opinions change in the middle of collecting a census. So it's not always better. So D, the clusters in cluster sampling should all look pretty much alike. I don't object to that one at all. I think that one's the correct answer. The last one, the sampling frame is the population of interest. It's close, but the sampling frame is the actual collection of possible participants in the survey. And so it's an actual list. If it was people, it'd be an actual list of people, which is not necessarily the same as a population of interest because some people don't make it onto that list. So they're not quite equal, but they're close. All right, therefore D is the correct answer. So pretty good with that one. And here's our agenda for the day. Doesn't look like much. We actually, we might be able to get through this pretty quickly. Standard deviation and variance. One thing right before we jump into this that I wanted to mention, it's not what I meant to mention yesterday, but it's worth talking about. The second half of statistics, because a lot of you in here are doing pretty well in the class, and so this might not matter for you a whole lot, but it is good to know that the second half of statistics is almost like review of everything we do in the first half. We have to build up a bunch of foundational knowledge during the first half. I think I might have mentioned something like this before. And then in the second half, we're doing what we call a lot of inference testing, and that's kind of repeating a lot of the skills that we have already developed. So every single day, I imagine it's going to half feel like, oh, that's something new I need to remember. And half, okay, we learned that before, I'm just using it again in a different context. So I think that's actually a good thing to be aware of so that you can kind of look forward to the fact that it's not just going to be constantly new stuff moving on to a different topic like we have to do right now. And we're pretty close to that point where it just starts all tying back together. So just be aware of that. The other thing, since there was a question in fifth hour, I want to repeat it here. The midterm, which will be 2 weeks and a day from now, it's not optional. Everyone will take it, but it's only going to count toward your grade if it brings your grade up. Otherwise, it'll just serve kind of as a progress check. So if you know your stuff and you're doing it really well, go ahead, do the best you can, and get close to 100% or 100% on it. But do the best you can on it throughout. Okay, let's jump into today's work, and we're going to start with camping. Woohoo! Camping time again. We went camping before, and we had to figure out how many loops you might stay in. Well, now this is a different campground. There are 10 campsites, and we're going to go camping for 10 consecutive weekends at this campground. Each time we go there, we get a random campsite assigned to us. So run a simulation to determine how many of the campsites you will stay in over the following 10 weeks. So my question for you guys is, how would you set up this simulation? Those are some interesting thoughts. I think we can develop those further. That's a good point. Okay, I feel like we're getting close to a simulation that's going to work. So maybe just, can someone summarize what we've talked about so far? I just want you all to be aware, this is the class that I record for the review. So
you should like assign.
Go ahead.
You should like assign each of the campsites a number between 0 and 9, and then get like a random number value thing and do stuff.
okay, there you go. That's a good start to it. Random number generator. We could go 0 through 9. Each number would represent. So what's great about the 0 through 9 is if you only had a random digit table, that works. You could do 1 through 10 if you have your calculator. You can set whatever range you want. Okay, so random number generator. Each number corresponds to a different campsite. So what do we do from there?
Do it 10 times.
There you go. Run that 10 times. All right, and that's good. So I'll just put times 10. All right. I know that would not be a FRQ appropriate way of describing it, but that gets the point across. What's our response variable in the simulation?
The campsite.
What about the campsite?
The number of campsites they at.
There it is. The number of campsites that you end up at. You could theoretically be assigned to the same campsite 10 times in a row. You could go to a different campsite every time and end up at 10 different campsites. So we want to figure out the response variable, or we want to figure out how many of those there are. So number of campsites. I'll just put CS right here for campsites. All right. So I want everyone to run the simulation once, and I'm going to do the same thing. So just to remind you how we do that on the calculator, you can do this one of two ways. We're going to use random. Oops. We're going to use rand int, random integer. Now you can do this one of two ways. Like if you're using 0 through 9, that's fine. You can even plug it so it's 1 through 10, so it matches up with the campsite numbers. You can also, if you want, put another number here to run it 10 times. Or if you don't like that option, you just want to do it 10 times in a row, then just leave it like that. It'll just give you a random number and just hit 10 times. So I'll run this like, if you know what you're doing, you can just go ahead. But here's how I'll run through a simulation of it real quick, just in case there's any confusion on how you're going to record your responses. So random number from 1 through 10, I put that in my calculator. I got a 7, so I'm just going to put a tally mark there. I got a 1. I got an 8. That's third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So there's all 10 components of my simulation, and it looks like I stayed at these campsites. So that was 7 different campsites. That's my response variable. So I want you guys to run through that. I'm going to move us over to the next page where we've got a number line. We can create a dot plot out of this. Well, okay, you'll still have the chance if you're trying to finish that up. It looks like most people have answered. There we go, we're getting a little bit added. So we want to create a probability model for this simulation. And it looks like currently 1, 2, 9, and 10, we didn't get any results for. So I'm just going to ignore those results. And so I'm going to come up with, oops, a probability model. We've got X and the probability of X. And now all of the different outcomes that we actually have had happen. We've got 3. Let's see, we got 6 here, so split that up evenly there. So 4, 5, 6, 7, and 8. All right, so in both of my classes, no one got a 1, 2, 9, or a 10. Well, I don't think so, at least. It just didn't work out that way. So if I look here, that's 2. If I look here, that's 3, 4, 4, 4, 3. Oh my gosh, this is almost like if I was to fake data, you know, it would look like that almost. Maybe if I had 5 in that for number 6. All right, we've got a grand total of 2 plus 3 plus 4 is 9, plus another 11 is 20 responses right here. You can double check my total. Yeah, that looks right. So if that's true, then I've got a 2 in 20 probability of 3, 3 in 20. We can just go down here, 4 and 20, 4 and 20. You can simplify it if you want, but it's really not super important to simplify this. And 3 and 20. We could convert it into decimals if we like. And, you know, it's your choice. When it's 20, that's an easy thing to do. So that's going to be 0.1, 0.15, 0.2, 0.2, 0.2, and 0.15. All right, so that might be a little easier when we're using some calculator work here in a second. All right, let's find the expected value. This is what we talked about yesterday. Expected value is, I'll put it right here. First of all, it's the same thing as your mean. And a lot of times it has that subscript X to show it's the mean of a random variable. And it's gonna be your value 3, like each outcome times the probability of it, so 0.1, plus 4 times 0.15. Okay, this is yesterday, so if you know what you're doing, you can go ahead and start plugging in the calculator. I'll just finish writing it out for completeness sake. All right, now, and as soon as you have the actual number, I'll just put this right here. Expected value equals, and someone can plug in what that value is going to be. So this is our expected value, and here's what's a good thing to know. In 5th hour, we had a different data set, of course, but it was 5.7272. This is basically just repeating. So good to know. We're getting consistent results. Okay, so there's our expected value. We're going to keep it at 5.7. All right, now let me actually go back. I need to do something in just a second. I need to take a picture because we're going to come back to these probabilities, and you probably have them written down, but I don't. So I'm going to take a picture of what all these probabilities are because I might forget between now and then. And I'll clear all this stuff off the screen. So we found the expected value. That was yesterday's kind of work. Today, we're going to find the standard deviation. We are going to calculate the standard deviation by hand one time. We're only going to do this by hand one time, but it's worth it to see it. Now, this is standard deviation for when you have a data set, just a bunch of quantitative data, and you want to get the standard deviation. It's the average distance. Conceptually, it's the average distance away from the mean for a data set. So any given data point is likely to be the standard deviation away. We find that by getting the average of the differences between the mean squared and add it all up. Okay, it's going to be a little different for a random variable because we're going to get weighted distances away. We don't have a bunch of data points here. We have 6 outcomes with different probabilities for each outcome. So we can't just divide by n. All right, so we're going to run through this, and you might have gone through something like this before when you were doing something in the past with standard deviation or mean absolute deviation. So the first thing we want to do is get the distance from the mean, and we're going to keep it, well, we don't have to worry about this, is 5.7. So now we didn't have 1, 2, 9, or 10 as outcomes. We did have 3 through 8, so I can just start all of these, I can just subtract 5.7 from to get the distance from the mean. All right, so 3 minus 5.7 will be negative 2.7. I know you guys, you don't have to completely copy this chart down right at the beginning. You can just kind of go down the first column and get this stuff done. And I will let you guys fill in this table. Okay, so very good. The first column, pretty straightforward. This is the distance from the mean. We want to square that. And so we'll just take each value and square it. We're going to end up with only positive numbers, so you don't need to worry about the negative. And, you know, I'll just put the first one in, 7.29. You guys can fill in the remaining values. All right, so we've got that. And so what we're doing is, the reason for squaring this is because this helps out with other statistics down the line. So we can just square that. Now this is the distance that 3 is away from the mean squared, but we don't have equal probability of only having 3 campsites. So we want to put the probabilities of that. You might have the probability model on your page, but I did not say, but I think it was 0.1, 0.15, 0.2, 0.2, 0.2, 0.15. So that looks right. So I just copied that from a probability model. So now what we want to do is get the weighted distance, which is really just multiplying that together. So that first one's going to be pretty simple, 0.729. And you guys can fill in the rest of the table with the other weighted distances. Okay, so assuming that all these numbers are correct, we didn't make a mistake anywhere, then this is the weighted distance. I'm just going to make sure we know that's the decimal point right there. And so we can just add these up, and what we're going to get is the total right here. And I'll talk about what that total is, but yeah, we can add that up. 0.729 plus 0.433 looks like 5 plus 0.098 plus 0.018. Is this really fascinating, getting to add up decimals as a class?
Yeah, I'm stoked.
Okay, I'm right there with you. 0.241 is what I got. I don't know if, or sorry, 2.41, whatever I said. That's what I got when I added it all up. So there we go. Now this, and we're going to come back to this, this is the variance. In fact, I'll go ahead and describe what it is, if I can spell it. So the variance is our total variation. So we found the variation of all of the outcomes, right? And then we just added it all up. So this is kind of the total variation that's present in our data set in this random variable. Now what we want to do is, well, actually, I kind of want to run through what we've done. I meant to do this along the way. So right here, we took a data point and we subtracted the mean. So that's going to be just any one of our random outcomes minus the mean. I should put sub x right here. And then once we did that, when we moved to this column, we squared it. So I'm going to do that right here. But we only wanted to get the weight, the proper weight of that distance. So we multiply by the probability. So now it's going to be multiplied by the probability of that particular outcome. And we got our weighted distance as a result. And now what we did right here for variance is we added them all up. So this is going to be the sum of all of those distances squared times the probability. Good, we're good with that. Now the last thing we want to do for standard deviation is we want to take the square root of this whole thing. And luckily we have the number right here. We just need to get the square root of 2.41. All right, so 1.552. And we're in the ballpark with that, with some truncation. You know, we probably got a little bit off, but the standard deviation of this random variable is 1.552. So on average, you're going to be within 1.552 or so of the average, the expected value of 5.7. And it's worth saying right now that we just found a model that we can use, right? We have a mean and a standard deviation. We already know what we can do with a mean and standard deviation. Okay, so let's jump ahead. That is a by hand calculation of standard deviation. Now we have our formula. I'll erase all this junk out of the way. And that will look familiar. That's what we just wrote down. So it's just important to know what this formula is referring to. So we basically, before the square root, we're getting the total amount of variation in the data, and then taking the square root of it to get the standard deviation. Pretty fun. Variance is the square of standard deviation. It's just, again, like I said before, it's the total amount of variation in the data. This is going to matter a lot more tomorrow when we're looking at the rest of chapter 16. So if you've already read it all, you already have some idea about how variance comes into play. We're going to look at a little bit today, but it's just worth kind of conceptually understanding it for right now. And the only difference between this and what you just saw is there's no square root. And so this is your standard deviation squared. Okay. So now it's a lot easier to do all this. That's the last time you're going to calculate expected value. And well, it's not the last time you might do expected value by hand, but it is going to be the last time you do a standard deviation by hand. All right. So the easy way of doing this, we've got a different scenario. This is some carnival game. You can here are all the outcomes and the probabilities. You have a probability model. So what you want to do is you want to create a list on your calculator, two lists on your calculator. One of them is going to be the outcomes. The other is going to be the probability of each outcome. So you might put it in list 1 and list 2, or yeah, that makes the most sense, I guess. I'll give you a minute to do that. All right, now I hope you guys have had plenty of time to get those two lists input, and some of you already jumped ahead and saw what to do next. Well, you've already used one variable stats. That's you hit stat, you go over to calc, and then one variable stats. But the difference this time around is we always skipped over that frequency list. Now we're going to use it. And your second list that you created is the frequency of each outcome. So there you go. Your outcomes will be list. Your probabilities will be your frequency list. It'll calculate. You will notice something's a little different about this when you calculate it. I ran the wrong numbers, sorry. Not that it matters. Anyways, you get outcomes from this, and you're gonna notice that you don't see S sub X, which is your sample standard deviation. That's what we always used before, but here they only give you sigma. Now remember, your sample standard deviation, among other things, you know, it's a square root function, and it depends on n-1 as your part of the calculation. We don't have any n's when we do this. There's no number of data points. This could be 100 data points, it could be 1,000 data points, right? So we have a different formula that we use for the standard deviation. And so knowing that, it just gives us sigma of X. Okay, so not a big deal there, but just worth being aware of. All right, so you already had, I didn't ask you what those were, but here's what I'm gonna do. Before we get started on this activity, if you guys could, down here, write what the mean and the standard deviation was for that data set. Or you can just tell me, what's the mean, sorry, the one that you already did, this one up at the top, not the new one. All right. So I think the mean, I got something a little different than that. It might have been a number got put in the list wrong. Okay, there it is. So yeah, I didn't ask you guys what it was before, but hopefully you saw negative 0.55 and 13.489. And just real quick before we jump into this again, how can we interpret that negative 0.55? What does that mean? Okay, so maybe the way that we want to think about, oh, were you going to say something?
No, you can go.
Is it your expected amount of prize money that you'd get?
Perfect, yeah, it's kind of your expected winnings over the long run, right? So if you played this hundreds or thousands of times, you'd expect to lose 55 cents each time you played. Okay, so that's kind of what the mean is. So we're going to do the same thing, but we're going to get a new mean and standard deviation of X. We're going to create different outcomes because now all the outcomes increased by 5. The prize levels have gone up, but it still costs the same amount to play the game. So there we go. Let's figure out those new outcomes. What's the first outcome going to be?
Negative 2.5.
Yeah. Well, I guess technically in this situation, maybe the cost goes down. Whatever the case, it's negative 2.5 now. The next, we don't need to belabor this. We can just see each of them is going to go up, not 20, 30, and all of them are going to go up by 5. So I want you to plug that into your calculator as a new list. You don't need to overwrite the old one. It doesn't matter if you do, honestly. Well, yeah, just go ahead and run a one variable stats with our new outcomes and write down what the mean and standard deviation are. Okay, this is looking good. We're getting those filled out. And just in case people were getting a little confused right here, I just want to stop to remind you, all you needed to do was create a new list with these outcomes. And then when you run your one variable stats, you'd pick, maybe if you put this in list 3 would be your list. Your probability, your frequency list is still the same. So that hasn't changed. So there you go. And you should see these results. So when we compare the original summary statistics here to the new ones, then what do we see has changed?
Just the mean.
Just the mean. And how has it changed?
It's increased
Increased by how much?
almost 5, 4 and 4.9.
It's actually gone up a full 5. So yeah, we can just do kind of subtraction between those two to see that it went up the 5, that constant that we added everything. So everything goes up by 5. That means our mean went up by 5 as well. The standard deviation, no difference there. Okay, so this is we're kind of learning the properties of adding and subtracting a constant. This should look familiar. If you remember when we were transforming our normal distributions, we could shift this, to the left. And of course that would change our measures of position like mean, median, mode, max, min, stuff like that, Q1, Q3, but it never affected our measures of spread. Our standard deviation, interquartile range, those stayed the same when we moved it around left and right. So this is kind of the same. You think of it as just a shift. All right. So now we're going to do something a little different. We're going back to the original distribution, the original probability model. If I can get rid of these markings. And now what we're going to do is we're going to multiply each outcome by 2. All of them double. Your winnings increase, but so do your losses. So we can fill this table in real quick. So if you want to, well, whatever. We know how to double things. I'll just do it real quick. So there it is. There's our new outcomes. You can create another list or override any of them that you want, except for the probabilities, and run a one variable stats with that and find out what the new mean and standard deviation for your random variable is going to be. All right, so there you can see how is this changing. If this is our original and this is the new, what's happening to our mean?
It's doubling.
It's doubling. We multiplied it by 2. What happened to our standard deviation?
It also doubled.
It's also doubling. I should put maybe x2 because that looks like 0.2 when I do that. So that's doubling as well. All right, we've got our properties now for multiplying or dividing by a constant. Again, to go back to the analogy of our normal distribution, when we multiplied or divided that by a constant, it would, in essence, what it's doing is it's changing the shape of it a little bit, but it is changing the spread of the data. Okay, so that would affect everything, your position and your mean, median, mode, or sorry, and your like standard deviation and interquartile range. Okay, good times with that. Let's wrap this up and look at a few practice problems from the book. So there we go. This is the result. Now the part right here in this kind of bluish color, this is from the textbook. So they use some slightly different things maybe than we were looking at before. Whatever, they just use slightly different notation. All right. Oh, I don't want to do that yet. So we've got our expected value when we add or subtract a constant is just the same as the original expected value plus or minus that constant. So that makes our job easy. If we have a standard deviation where we're adding or subtracting a constant, nothing changes. It's the original standard deviation of the random variable. All right, right here, we're multiplying by a constant, but instead of doing that, why don't we just pull the constant out, take the original expected value, multiply that original by whatever constant we're multiplying. And there we go, we're good. The last thing here is when we've got the standard deviation multiplied by a constant, we can pull that constant out and we're gonna multiply by the standard deviation, constant times standard deviation of the original. So it's a summary there. It's only gonna help you if you understand what this notation means and you understood those examples, but it can help. Now we're gonna look closer at these two. We only introduced variance a little bit today, but if we remember, variance is just standard deviation squared. So in this case, when we're adding or subtracting a constant and the standard deviation doesn't change at all, well, neither would the variance because it's just the same standard deviation as before squared. So this variance won't change at all. All right, but now we get this, which at first might seem like a little bit of a weird result. And what I might do here is I'll change this to an A and an A. So we're using the same things. So your variance is your standard deviation squared. So that's going to be A times the standard deviation of your random variable squared. When we do this, we have to square both the standard deviation and the constant. So that's how we end up with this equation. Okay, not super complex mathematically, but it can be something that you overlook. So try and remember that. And tomorrow, like I said, is when we're going to be dealing with variance a lot more. So we will wrap up today just by looking at a few practice problems. I'm only going to look at one of these real quick. So they give us two random variables with a mean and a standard deviation. They've already done all the calculations, but now we need to figure out what happens when I multiply this random variable times 2 and then add 20 to it. And again, this should look somewhat familiar. You've already seen problems like this in the past, but dealing with distributions and different normal models. So now I can do 2 times y. Well, I need to find the mean, I guess, of y, not x. So that's going to be 2 times the mean, which is 12. I'm using the wrong number. 2 times 12 plus 20. And I just got this equation from right here. All right, so when I do that, 2 times 12 is 24, plus 20 is 44. Great, we got 44 as our new mean. When we're finding the standard deviation of y, it's going to be 2 times, there's the standard deviation, 3 plus 20, except, like we just saw, adding and subtracting a constant does not change my standard deviation. So I'm going to cancel that out. Like, I don't use it at all. So really, it only changes to 6. Okay. So not super complicated there. Hopefully that makes sense. The next ones have a little bit more going on. Your company bids for 2 contracts. You believe the probability you get contract number 1 is 0.8. If you get contract 1, the probability you also get contract 2 will be 0.2. And if you don't get it, the probability you get contract 2 will be 0.3. Okay, so here are the probabilities they gave us. They gave us the probability we get contract 1. All right, and now the next probability is 0.2, but how would I describe that probability?
It's conditional.
It is conditional. So it's the probability of what given what?
Contract 2 giving contract 1.
Okay, probability contract 2 given that we got contract 1. And the last one is 0.3. And how would we describe that probability?
Conditional.
Conditional. What given what?
Contract 2 if you don't get contract 1.
There you go. So I'll just put the complement of 1 up there. There it is. So what this should automatically make you think of is the fact, oh, it's conditional probabilities, which means I'm going to need to create a tree diagram. And we will, and we'll do that in just a second. But the first question, are the 2 contracts independent? And what do we think?
No.
Okay, does anyone have it's kind of a tricky question. Does anyone have an explanation as to why they're not independent?
Wouldn't they be independent though? Because if you don't get contract 1, the probability of getting contract 2 goes up.
Well, you're talking about something that's important, but the conclusion we have is that whether we get 1 or don't get 1, that changes our probability, right? If these were independent, then the outcome of getting contract 1 would have no impact on getting contract 2. But because it does, and it changes the probability, we can say that they are not independent. So, I mean, just the shorthand is, these are not independent because the probability changes based on the outcome of contract one. All right, so I'll just put a no here. I won't write that full thing out. All right, what's the probability we get both contracts? The next question is, what's the probability we get no contracts? I think the easiest thing to do right here is create a tree diagram out of it. So we could get contract one, we could not get contract one, and that breaks down like so. We could get contract two, we could not get contract two. And that depends, for some reason, on how we do with contract one. And let's see, this is 0.2 right here, which means this is 0.8. This is 0.3, which means that's 0.7. All right, so now we can figure out all the probabilities going on here. I'm just gonna do it real quick. 0.16, 0.64, 0.06, and 0.14. And remember, if you do this right, these two right here should add up to your 0.8. Okay, so now we've got this. Now we're going to come up with our probability model. So we have different outcomes with different probabilities. Let X be the number of contracts you get. So what are the different outcomes we could get?
You get 0 contracts. You
You
get
get
1 contract, and then 2 contracts.
0, 1, or 2. Those are the only outcomes. And we can see right here, if we can read the tree diagram, we know what that is. Here is not getting contract 1 and not getting contract 2. So that's the only outcome where we don't get any contracts. So it looks like 0.14. I'll go the other extreme that says we get both. The only way we get that is if we get contract 1 and we get contract 2, which is going to be 0.16. So if you didn't create a tree diagram for this, you can find the probability of 0, find the probability of 2. Probability of 1 is going to be everything else. But of course, we can just add these two up and see that's going to be 0.7. All right. So anyways, we've got a probability model. Fantastic. Now we can find the expected value and standard deviation. Let's go ahead and do this one. You can create lists in your calculator. You can find out what the expected value and standard deviation are. I'm going to put a spot for that right here. And whenever you guys get answers, you guys can put what those answers are right there. Okay, and I know some people take a little longer getting the stuff put in their calculator. Those are the answers. If everyone is comfortable with this problem and what we had to do, we'll move forward. But are there any questions on this?
I have one.
Yeah.
So standard deviation, would we have to use the equation that we just got?
No, that the complex one with the square root and everything?
Yeah.
No, we don't have to use that. You can do it by hand, it's just very time consuming. So
Okay.
I just plugged it in the calculator and
Okay. I was wondering that because I was wondering how someone found the mean that fast.
Oh, okay.
Mm.
No, that's a good question. Okay. So yeah, just in general for everyone out there, just make sure you're comfortable finding that on the calculator, and if you're good with it, that's all good. We're gonna do one more, and then that will be it for today. We might be done somewhat quickly today. All right, in a litter of 7 kittens, 3 are female. You pick 2 kittens at random, create a probability model for the number of male kittens you get. And then we just need to, so I'll just say this. If you can find a probability model of any random variable, then you can just plug that in as lists on your calculator. And these 2 questions are very easy. So the hard part of this problem is creating the probability model. And it's not even necessarily hard once you know what you're doing, it's just time consuming. So let's go ahead and do that. So I'll ask again, what are the outcomes of this scenario?
Two males.
2 males?
Um,
Actually,
male
I
and
need to write
female.
that. Yeah, so I'll just put 2 males, 1 male, or
0 males.
0. And the reason I'm saying it is 2 males, 1 male, 0 males is because the probability model for the number of male kittens. So they're asking for just the number of males. All right. So there's different ways we can approach this. We can create a tree diagram. We could just find the probability of getting 2 males and no males, and then everything else is the probability of getting 1 male. So we have options. So let's, first of all, find the probability of getting a male first and a male second. So it's really a male, oh, to clarify, that's male second on condition that we got a male first. So just to simplify this a little bit, what are the 2 numbers that I'm going to multiply together to get that?
4 out of 7 and 3 out of 6.
All right. Does that make sense for everyone? So if there are 7 kittens, 3 are female, that means we're starting off with 4 out of 7 being male. Once you've drawn a male out, there's only 3 males left out of 6 kittens. So there we go. We can multiply that and find the probability. This is basically going to be the probability of 2 males. And whatever decimal that is, you guys can fill that in. There it is, 0.286. So that's the probability of 2 males. I'm going to go ahead and put it right here. Now we've got, I'm going to skip over to probability of no males. Remember, all or nothing is the easy one. It's that at least one that gets a little more complicated. So, I mean, it's really not too bad for this. We're in this particular scenario. But so the only way that we get no males is if we get a female and a female. But given that we got a female the first time. So someone different, put up the numbers we're multiplying to get this outcome. There it is. We have 3 females to start off with. If you pick one, there are 2 left out of the 6 remaining kittens. So 3/7 times 2, 6 gives you your answer. So as soon as you got that, someone can fill that in. There we go. 0.143. Fantastic. Now we technically have 2 outcomes for the one, which is why we can't just do one quick probability calculation. So we have the probability of getting a male first and a female second, given that we had a male first. And we also would need to do the probability of female first and a male second, given that we had a female first. Those are different probabilities, and we'd have to add these 2 together.
Couldn't we just do 1 minus like the sum of the 2 and 0?
Perfect. And that's what I was going to get to. We can, if we're confident we did these. Oh no, that's great. I'm glad you thought of it. So don't apologize. So if we're confident we did these 2 right, then just like Jacob was saying, we can just do the complement of those two, and that saves us some time. So if anyone finds that number, you can go ahead and add it to the chart. Okay. Of course, just to make sure we're doing it right, we can just add across and make sure we get, so that's going to be, yep, that's 100%. There it is. All right, we have our probability model. The rest of it's pretty straightforward. Okay, fun times. So good work on all of that. I'm not going to make you guys do this right now. If you know what you're doing, you don't really need to go through and do that extra work at the moment. So here's your homework. For 25 and 27, the only ones that you can do based on what we did today are A and B. If you read the chapter, you want to try C, D, and E, you can, but that's something we're going to look at tomorrow. Okay, we'll finish up chapter 16 tomorrow, and besides that, we're getting out about 30 minutes early. If you have questions on anything, you need to stick around, please feel free to do so, and have a wonderful day otherwise.